Your heart is squeezing with enough force to shoot blood 30 feet into the air. Every single second, without a single thought from you, your body is making thousands of micro adjustments to keep that pressure inside your blood vessels within a razor-thin safe zone. Too low, and your brain shuts down within seconds. Too high, and your arteries could literally explode, or your heart could give out under the strain. Billions of people worldwide are walking around right now with blood pressure in the danger zone. And most of them have absolutely no idea. So today, we are going deep, all the way into the molecular machinery, the neural circuits, and the hormonal cascades that your body uses 24 hours a day, 7 days a week, to keep you alive. First, let's make sure we all understand what blood pressure actually is, because most people get this wrong. Blood pressure is simply the force that your blood exerts against the walls of your arteries as your heart pumps it around your body. When we say 120 over 80, that's two numbers. 120 is the systolic pressure, the peak pressure when your heart is contracting and squeezing blood out. 80 is the diastolic pressure, the baseline pressure when your heart is relaxed and refilling between beats. And here is why this matters. Your arteries are not rigid metal pipes. They are living, elastic structures. If the pressure stays too high for too long, those walls stiffen. They crack, plaques form, and you are heading straight toward a heart attack or a stroke. But your body has built a breathtaking system to prevent exactly this from happening. And that system has three major control centers: your nervous system, your kidneys, and your hormones. All three work together all the time. Let's explore each one. The nervous system is your body's fastest blood pressure controller. It responds in seconds, sometimes in milliseconds. The moment you stand up from a chair, gravity tries to pool all your blood in your legs. Your blood pressure in the upper body drops instantly. Without immediate correction, you would black out every time you stood up. This almost never happens because your body detects the drop within milliseconds. These sensors are called baroreceptors, pressure-sensitive nerve endings that live in the walls of your aortic arch and your carotid sinuses, right in your neck. When pressure is normal, these baroreceptors send a constant stream of signals to the brain, essentially saying, "Pressure is fine, keep everything stable." But the moment pressure drops, like when you stand up, those signals slow down or stop, and that silence is the alarm. The cardiovascular control center sits in the medulla oblongata, the most ancient part of your brain, right at the base of your skull. It receives the baroreceptor signals and coordinates the entire response. When pressure drops, the medulla fires two simultaneous commands. First, it activates the sympathetic nervous system, your fight or flight system, to squeeze blood vessels tighter and speed up the heart. Norepinephrine, the sympathetic neurotransmitter, hits alpha receptors in blood vessel walls, causing the smooth muscle to contract. The vessel narrows, resistance increases, pressure rises. At the same time, norepinephrine hits beta-1 receptors on the heart muscle, increasing both the rate and the force of each heartbeat. More blood pumped per minute equals higher pressure. The second command from the medulla is to reduce parasympathetic signals to the heart. The parasympathetic system, your rest and digest system, normally keeps your heart rate calm and slow. Turning it down lets the heart speed up even faster. Within 2 to 3 seconds of standing up, all of this has already happened. Your blood pressure has been corrected before you even notice the change. This is called the baroreflex, and it is one of the most elegant feedback loops in all of biology. If the nervous system is the sprint, the kidneys are the marathon. They don't respond in seconds. They work over hours, days, and even weeks to set your long-term blood pressure baseline. Here's the key insight that most people miss. Blood pressure in the long run is fundamentally a question of fluid volume. The more fluid in your blood vessels, the higher the pressure. And your kidneys are the sole gatekeepers of how much fluid stays in your body. Every single minute, your kidneys filter about 1 liter of blood. That's over 1,400 liters per day. From that, they precisely decide how much water and salt to keep, and how much to flush out as urine. The functional unit of the kidney is called the nephron. You have about 1 million nephrons in each kidney. Each one is a microscopic filtration machine that runs 24 hours a day for your entire life. When blood pressure drops, the kidneys don't just passively conserve water. They trigger one of the most powerful hormonal cascades in your entire body, the renin angiotensin aldosterone system, or RAAS. It starts with specialized kidney cells called juxtaglomerular cells. When they detect low blood pressure, or low blood sodium, they release an enzyme called renin directly into the bloodstream. Renin is a protease, a protein-cutting enzyme. It targets a protein called angiotensinogen, which is made by your liver and floats constantly in your blood, just waiting to be activated. Renin cuts angiotensinogen into angiotensin I, but angiotensin I is still mostly inactive. It needs one more conversion, and that happens in the lungs. Angiotensin II is one of the most potent vasoconstrictors in your body. It binds to receptors on blood vessel smooth muscle all over your body and causes them to contract hard, raising blood pressure almost immediately. But angiotensin II doesn't stop there. It also travels to your adrenal glands, two triangular glands sitting on top of your kidneys, and triggers them to release a hormone called aldosterone. Aldosterone is a steroid hormone, which means it works differently from most hormones. Instead of hitting a surface receptor, it enters your kidney cells directly, goes into the nucleus, and changes which genes are being expressed. Those new genes produce more sodium channels and more sodium-potassium pumps in the kidney tubule walls. The result? The kidneys absorb more sodium, and water follows sodium by osmosis. More water retained equals more blood volume equals
The entire
blood pressure.
RAAS cascade,
RAAS
from renin
cascade,
release to increased blood volume, can restore blood pressure
over a period of hours to days. It is the reason why the drugs that block this system, ACE inhibitors and ARBs, are among the most prescribed blood pressure medications in the world. RAAS is the biggest hormonal player in blood pressure control, but it's not the only one. Your body runs multiple overlapping hormonal systems to make sure pressure is always regulated. Epinephrine, adrenaline, is released from the adrenal medulla during stress, exercise, or emergencies. It amplifies everything the sympathetic nervous system is already doing, but through the bloodstream instead of nerves, so its effects last longer. ADH, antidiuretic hormone, is released from your hypothalamus when blood pressure drops or blood becomes too concentrated. It travels to the kidneys and inserts special water channels called aquaporins into the collecting duct walls, causing your kidneys to retain water. But here's a beautiful counterbalance. Your blood vessel walls produce a gas called nitric oxide, and it does the exact opposite of all these constrictors. Nitric oxide causes blood vessels to relax and widen. This is why exercise lowers blood pressure over time. Physical activity increases blood flow, which increases shear stress on vessel walls, which increases nitric oxide production, which makes your arteries more flexible and relaxed, even at rest. Here's something that genuinely surprises people. Your heart is not just a pump. It is also an endocrine organ. It produces its own hormone to lower blood pressure. When blood volume gets too high and the atria of your heart get overstretched, specialized atrial cells release a hormone called atrial natriuretic peptide, or ANP. ANP is the body's emergency pressure release valve. It directly causes blood vessels to dilate. It tells the kidneys to excrete sodium and water. It suppresses renin and aldosterone. It is the opposite of RAAS, and the two systems constantly balance each other. Now that you understand how perfectly designed your blood pressure system is, let's talk about what happens when it breaks. Because for over 1.3 billion people worldwide, it has broken. Hypertension, high blood pressure, is called the silent killer because it has no symptoms. You can have dangerously high pressure for years and feel completely fine. Meanwhile, the damage is accumulating. The damage starts in the endothelium, the single cell layer lining every blood vessel in your body. High pressure creates turbulent blood flow, which tears and inflames the endothelium. Those inflammatory signals attract immune cells, monocytes, which burrow into the vessel wall and become macrophages. They eat oxidized LDL cholesterol and become foam cells, the first step toward plaques. Over years, smooth muscle cells migrate in. A fibrous cap forms, and a full atherosclerotic plaque develops, narrowing the vessel and making it rigid. If that plaque ruptures, a clot forms instantly. If the clot is in the heart, heart attack. If it's in the brain, stroke. Sustained high pressure also forces the heart to work harder against greater resistance. The heart muscle responds the way any muscle does to extra work. It grows. But cardiac hypertrophy is dangerous because thicker walls mean stiffer walls, and stiffer walls can't fill properly.